Howdy. In this video, we're gonna apply the method of sections to solve for the forces in the members of these truss over here. Now, I already did a video on the same truss over here using the method of joints to solve for the forces in all the members. Here's the answers that we got using the method of the joints. Again, when we apply the method of the sections, we should get the same answers. That's if, of course, I didn't make any mistakes with the method of the joints, but we should get the same answer. So I'm leaving them here. I'm also gonna try to link that video somewhere in the cards, or at least at the very end of the video, I'll put that link to that one for the method of the joints so you can see how we got all of this. I'm not gonna bore you with doing the first step of using the method of the sections, which is the same step that we usually do for the method of the joints. Which is to solve for the support reactions. Yes, there are some instances where you don't need to solve for the support reactions. There's some special kind of trusses. In this one, I'm going to try to solve or do a couple sections here. So we look at most of these members. So naturally, what I would have done anyways is to solve for the support reactions here at the pin and at the roller here at G. In short, what we did is we sum moments at point A to solve the roller at G, then we sum moments at point G to solve for the AY component, and then we sum forces in the X to get this guy. When we look at the truss over here, probably some of the difficulty that comes with the truss is sometimes they just give you distances as no angles. I purposely picked the truss where the angles are easy, so that we're not kind of concentrated with the angles, but more just with the process of what the sections are. Anyway, so in this truss, the distance here between the bottom joints is 3 millimeters. The vertical distance is 4. So we can very easily form a slope triangle for the slanted members, 3, 4, 5 over here. And we'll use that. So let's go ahead and start applying the method of the sections. Okay, so when we're applying the method of the section, usually the problem is going to ask for the forces in 3 members. Why 3? Because we know that when we cut a truss, right, the maximum members that we want to cut through is 3, because we can only solve for up to 3 unknowns. And if you remember, the equations that we have is that the sum of the forces in the X must be equal to 0, the sum of the forces in the Y must be equal to 0, and the sum of the moments must be equal to 0. This is a little different from the method of the joints, because in the joints, all the forces intersect one point. It's a concurrent force system, so there's no possibility that a moment could be generated. When we take a cut or a section, now we're dealing with a rigid body, so we need to account for any rotations with this moment. Again, I think this method is beautiful. I usually prefer the method of the sections to determine the forces in the member. Even if I do the method of the joints, I'll do 1 or 2 cuts with the method of the sections, because very quickly I can determine the forces there. And I just personally trust the method of the sections better. Why, you ask? Well, part of the reason is when we do the method of the joints, we're taking the answers from one of the members into the next Freebody diagram, and then from that one we'll go to the next one. So the likelihood that you make a mistake and that it propagates throughout is, at least for someone like me, high, and there's really almost no good reason to figure out if you've gone right or wrong until you get to the very end. With the method of the sections, we have 3 equations. If we pick the right points, for example, to some moments, we can end up with 1 equation, 1 unknown, so we will be 100% sure that the answer that we get is the correct one. Again, the goal in this one was to solve for the forces in all the members. So I'm going to start just slicing the truss. So how about let's take a first slice over here in this truss. If I have this one, again, I want to cut through maximum of 3 members. So I look at this one and it's screaming to me like, go ahead and cut it down here vertically like so. So let's go ahead and do it. Let's assume I cut the truss here, right? If I cut the truss, I would have here the left-hand side and the right-hand side. On the right-hand side, I have this GY and the X and the Y components of that force. So that's 1, 2, 3 forces. If I stick to the left-hand side, I would only have these two applied forces. So I would cut it there. And the most simpler, right? Because here I have a lot of distance. This other section is a lot quicker, right? So I'm going to cut again right here. We're cutting there, and then I'm going to draw that free body diagram of that section. So the FBD is going to look something like this. So I have point B, right? I had a member going horizontal, B to C. So I'll draw a little bit of it, and then kind of it stops there, and it goes down. So this is point A. Let me put A here. And then there's member AH that goes that way until I get to kind of the cut. And then this one that goes from A to C, it's at an angle. And let's assume that point C was here originally. So this member was pointing there like so, and then we made the cut right there. So let me go ahead and so this here would be considered the outline of the body. Again, here point C is not on the actual outline of the body, but it can still be part of the free body diagram. Whenever I cut a member, the assumption or the convention, I should say, is to go ahead and whenever we cut, we expose the internal lobes. We're going to point those arrows away. And again, if an arrow points away from a member, just like when an arrow points away from a joint, away means tension. So I'll put here, hey, I have a force here that goes from B to C pointing away. So I'm assuming tension to begin with. I'll assume tension on the member A to C to begin with. And I will assume tension on the member from A to H to begin with. So what else I need on the free body diagram? Well, I have all my unknowns. Do I have any knowns or given or applied forces? Yes, I got two. I got one here horizontally pointing over here towards the left, 86.603. And a Y from that pin was pointing down with a magnitude of 0.32735. Okay? We're almost done. What else do I need on this free body diagram? Well, I need distances. So we get a green marker. Usually I use green for distances. This over here is going to be 4 meters. Right? Up to that line. And then from B to what would be point C originally, right? This distance here was 3 meters. So I got distances. Oh, I got here a member that is slanted or at some angle. So I need information there. Again, what I'm going to do is, look, the base of this right triangle, the base is 3. The height is 4. So the hypotenuse has to be 5. So I'm going to take advantage of this 3, 4, 5 slope triangle. I think I have almost everything. I have outline of the body, applied forces, reactions or unknowns, geometry. The only thing that I'm missing here is maybe an X and a Y axis. So I know which direction is X axis and which direction is X and Y axis. Once we have this, remember we have 3 equations of equilibrium. We can sum forces in the X direction, we can sum forces in the Y direction, and we can sum moments. How do you pick which equation to start with? Look at your unknowns, right? If we look at summing the forces in the X, BC, AC, and AH, they all have a component or all of it in the X direction. So if I sum forces in the X, all of them are going to show up. So that's not a good equation to start with. I will have 3 unknowns. If I sum forces in the Y, BC and AH don't contribute. AC is the only one with a Y component. That's a good one. It will be 1 equation with 1 unknown. So let's go ahead and do that one. Sum of the forces in the Y direction must be equal to 0. Again, if it points up, we'll say it's positive. So what do we have? We have AC, the vertical component. So we have AC. Again, but the vertical component of AC is 4 by 5. So we multiply here times 4 by 5. And that vertical component of AC, at least because I assume tension, would be pointing up. So that would be a positive force. What else is vertical? Well, just this other guy is pointing towards the negative y. So minus 32.735. And let me double check. I got nothing else that points either up or down. So the sum of those two forces must be equal to 0. We can solve for AC here very quickly. I move this to the other side and I'm going to get a positive 32.735. And then I need to divide both sides of the equation by 4/5. So divide by 4/5. When I do, I get a positive number. I get positive 40.91919. It's a positive number. So positive number means, again, that the direction that I assume is correct. Here, the direction that I assume for AC is away. Away equals tension. So I'm comfortable saying AC member is under tension. So if I go compare here with my previous results, I had determined AC to be 40.919 and tension. So we're starting on the right track over here. Anyways, back to the method of the sections. Now we know what AC is. I'm going to put a little check mark here because I know this guy. Next is what else would I do to solve for BC and AH over here? Well, we thought about forces in the X. That's not a good option. We already did forces in the Y. So next we're going to sum moments. So let's sum moments and make them equal to 0. Now when we sum moments, the question should always be about which point. Well, we need a point where we have two unknowns intersecting. So if I look here, I got two arrows, and if I follow their line of action, they're both intersecting at this point A. So point A is a very good point to do the sum of the moments. So let's go ahead and write that equation of equilibrium. We're going to sum moments at point A. Look at this. So because I'm summing moments at point A, this 86, this force, AH, and AC, they all pass through point A. So none of these here are going to generate a moment. The only one that is capable of generating the moment is this force BC. What is the distance? Well, it's 4 meters away. But you're going to see that that distance doesn't almost matter because this is the only force that could generate a moment about point A. However, we say the sum of the moments must be equal to 0, so that one moment must be equal to 0. The only way that this is going to be equal to 0 is if BC is 0. Right? So we did the method of sections here, and we found a member that has a force 0. It's called the zero force member. When I check here our previous answer, we had determined that previously, so we get confirmation BC. Well, not confirmation, but at least the two methods are agreeing. BC is a zero force member here. So we have this BC guy over here. We're still trying to solve now for AH. Here you might be tempted to say, well, I did forces in the Y. I already did a moment equation. So next I need to think in the X because I already know what those two are. And yes, it's a valid method. It's valid. If these numbers are correct, then you can go ahead and do that. But the problem is if any of these values were off, you made a fat finger mistake on the calculator, those are going to get transferred to that equation and you're going to get a just completely wrong value for AH. So try to sum moments again. Can you identify another point where two unknowns intersect? Well, I got these two at A, and then I got these two. See, if I continue their line of action, both of these would intersect at this point C over here. So we can sum moments at point C and make it equal to 0. This one is kind of weird for some students because we say, hey, I'm going to do a cut, right? I'm going to do a cut. And this point C is no longer on the section that I chose. So the point C itself or the spin, dismembers, they're not there, right? But nonetheless, if we follow the line of action, those two forces are going to intersect. They intersect at point C. So we can take advantage of that fact, right? That at that point, those two are not going to generate a moment and still some moments. No, we're not going to bring this 86 and 50 newtons at C and put them in here because those are applied to the right-hand section over here. We only care about the left-hand section and the fact that the two forces intersect at point C. Okay, so we already said BC and AC do not generate a moment because they pass through point C. What could generate a moment? Well, we have, for example, AH, which is the one we're trying to solve for. The force is AH. This is an A here. So that's the force. The perpendicular distance to point C is 4 meters. So AH times 4. Next, we need to ask, will it generate a positive or negative moment? Well, if I'm at pin C here, right, and AH passes here through the bottom, it's going to do this here. That's a counterclockwise or a positive moment. So this is a positive moment. Put a little plus there to remind me. So we have AH. Next, let's do this one here, 32.735. Right? Why this one? Well, because it doesn't pass through point C. It's actually a distance of 3 meters. That's the perpendicular distance. And again, if I'm at point C and this arrow here points downward, it's going to generate a counterclockwise rotation. So that would be a positive moment. Next, we have the 86.603 force. It's at a perpendicular distance of 4 meters. Here's the line of action, right? So that would be the perpendicular distance. It's 4 meters. And again, we're trying to see which rotation it would cause about point C. The line of action here is that direction. So if I go in that direction, it's going to swing whoop, like that. So that's a clockwise or a negative moment. And I think that's it. These two do not contribute, so I would have 1, 2, 3. 1, 2, 3. So the sum of those must be equal to 0. I can solve for AH member in this equation. Right? How? I would move all of this to the other side and then divide by positive 4. So I had negative 86. When I move to the other side, it's going to become positive 86.603 times 4 minus, because this moved to the other side, is going to become negative 32.735 times 3. And then all of that divided by a positive 4. We divide by positive 4, we get that AH is equal to 62.052. 62.052. And it's a positive number, so it means that guy would be under tension. So let me look over here, my previous answer from the method of joint, 62.052 in tension. So the two are agreeing. We're pretty comfortable now that these are the right values. But check this out. This is why I like the method of sections even better. What do I mean even better? Do you remember that we have this equation over here, some of the forces in the x direction that we haven't used? So what would happen if we actually sum forces in the x? Look, BC, AC, AH are going to contribute, right? So we're going to put it in and check if it equals 0. So how are we going to do this? Well, I'm going to say sum of the forces in the x. I'm going to look at the direction of these arrows, right? ABC, AC, and AH. They're all pointing towards a positive x direction. So I would have BC plus the horizontal component of AC, which is AC times 3 by 5, plus AH. And then what else is horizontal? This guy. This one's pointing in the negative x direction, so minus 86.603. And the question that we're going to ask is, does that equal to 0? Well, let's put the values. But before we do, right, we need to check over here. So BC here goes to 0. That's what we determined. AH is positive, so this here we're going to put 62.052. AC, however, we determined tension, so the original sense was correct. So this guy we're going to put positive 40.919. Okay, so we pull out the calculator. We got 0 plus 40.919 times 3 divided by 5 plus 62.052 minus 86.603 equals. And when I plug this in my calculator, the number that I get is 4 times 10 to the minus 4, or 0.123 and a 4. Right? This is rounding. This is right there from the rounding. That number is 0. So again, the beauty, or another reason why I like the method of the sections, is usually I can go back and plug it in one of these equations of equilibrium and check my answers. All of this equal to 0. Everything is in balance. Now I'm super confident that's the right answer. That's the right answer. That's the right answer. Alrighty. So I boxed in the answers that we confirmed with the method of the sections. I'm gonna do another section over here. Hopefully I'll do a third section. I might not solve all of these members with the method of the sections because my camera is running out of battery. But let's try another section real quick. So what am I going to do? For this one, I'm going to go cut at the other end over here. I will cut over here through 3 members. And let's see what happens, right? So what would that one look like? Well, I got this point E over here. This one comes down this way. And I got point F. And then I got a member here that was pointing down, right? So I'm going to assume tension or away. So this guy goes from F to G. This guy over here goes from E to G. And then this guy over here goes from D to E. What else we need? We need an x-axis. We need a y-axis. We need geometry. So the height is going to be 4 meters. If we follow the line of action of this guy, it's going to intersect at this point G over here, and that's going to be 3 meters away. Obviously not to scale. So we have outline of the body, we have some reaction forces. Next, let's put applied forces. And we look at this little bit of truss, there's no applied forces, so I got no givens. What in the heaven does that mean? Well, we'll figure that one out. And that's it. I got my axes. So next, I'm going to go ahead and apply the equations of equilibrium. Look at this. I got horizontal force, horizontal, and one is vertical. So if I say the sum of the forces in the y direction equal to 0, what do I have? Well, I'm going to have the vertical component of EG. Remember, we have slope triangle, 3, 4, and the hypotenuse is 5. Sum of the forces in the y, I would have minus. Why minus? Because the vertical component of EG points down, so minus EG. It's not all of it, right? Just 4/5 of it, 4 divided by 5. However, there's this one. Do I have any other forces up and down? The answer is no, that's the only one. So guess what? The sum of the forces, even if it's just one, must be equal to 0. The only way that can happen is if EG equals 0. So we just figured out EG is a 0 force member. We did the same here with the method of the joints. Boom, 1 down. Now we got 2 left. So what would we do? There's some moments where we have 2 unknowns. Point E is a good one. So look at what would happen. Some moments at point E must be equal to 0. These 2 do not contribute. I would only have FG, right? FG times 4 will produce a negative moment, but there's nothing else. So the only way that can be equal to 0 is if the actual force in member FG is 0. So FG 0. Oops. FG 0, AG, 0. And we need to solve for the last one, which would be DE. Well, if I sum moments at point G over here, remember these two are going to intersect at point G, right? I would only have one force DE at some distance. It's the only one that would generate the moment. The sum of the moments would be equal to 0. So the only way that can happen is if DE equals to 0. So we found out that DE is also a zero force member. The moral of the story on that one is maybe you don't remember how to identify zero force members. Go back to the lecture or the previous slide. I discussed how to identify them again by inspection. Even if you fail to identify them when we're doing initial inspection and you go ahead and start doing the free body diagrams of the joints as we saw in the previous video, or even if the section, like don't be afraid if you end up with a situation like this and all your members are 0. Right, these are off over here. There's no applied loads. There could be zero force members. All you will need to do is just verify, is there any applied loads in that section here? No. So that's it. Just don't make sure you don't miss anything. All right, so we've done the two ends over here. Now let's cut through the center of the truss, something like so that we can determine the forces in member CD, DH, and HG. Now, whenever we cut, right, we always get to pick between each of the two sides. So I have the left hand side and I have the right hand side. And so which one would you pick? Well, remember, we always want to pick the simpler side, the one that has the less forces, the less complicated geometry. This case, geometry is the same on both sides, so we're not going to decide on geometry. But look at the left hand side. We have 2 forces there, another 2 forces over here, where on the right hand side, we only have 1. So here we'll go with the section on the right hand. So if we draw the free body diagram, here's point D, E, F, G. There's a line going that way, and then DC, a little bit of DH, and HG. It's more or less where we make the cut. Remember, whenever we make a cut, we're going to put arrows over here pointing away. So we're assuming tension that goes from G to H. This arrow here goes from D to H. Remember, if we follow the line of action, somewhere over here is this point G. Last one is the top member. This is member CD. Over here. We're almost done. We need some geometry. This here is 4 meters. This is 3 meters. And from G to, from G, this point is H. Sorry. This is point H. That is 3 meters as well. What else do we need? Slope triangle. 3, 4, 5. We're almost done with this free body diagram. We want to make a complete one. We'll put our X and Y axis. It doesn't matter where we put the axis in this location. We can put it here, here, any point. Just generally I'm saying positive X, positive Y. Okay, so check the free body diagram. Do we have an outline? Yes. Do I have any applied loads? I don't. I forgot this one over here. So don't forget the force here at G. This is 82.735. Right? This is where you want to ask those questions. What does a free body diagram take? It's an outline. Got it. Applied loads. Okay. Just one over here, one done. Any reaction forces, or in this case your unknowns. We got the 3 of them. Now we need geometry, distances, angles, check, axes, X and Y, done. Perfect free body diagram. Let's go ahead and analyze it. Remember, we're trying to solve for these forces here in red. When we look at the forces in red, we have horizontal, right? Horizontal component and horizontal. So if I sum forces in the X, all of the three are going to show up. We don't want that. If we do some of the forces in the Y, only DH has a Y component, right? So that's good. So we're going to sum forces in the Y to begin with. Some of the forces in the Y direction must be equal to 0. What do we have in the Y? Well, we have the horizontal component of DH, right? So the force is DH. The vertical component here is 4 divided by 5. That's what we multiply, right, to get the vertical component. That force is pointing down. Again, we assume tension. Tension is pointing away. That's pointing down, so that's negative. Pointing up is this guy, plus 82.735. The sum of those two forces must be equal to 0. So we can solve for DH in this equation, right? By moving this 82 to the other side, it becomes negative. And then dividing both sides by 4/5. H is 103.419. So let's check our answers. The H, ABC, the GGH, 103.4, 103.419. We got agreement so far. What do we do now? So now we know what DH is, right? We know this guy. How do we solve for the other unknowns? Well, we said some of the forces doesn't work. We already did some of the force in the Y. Let's do some of the moments. Let's sum moments, but the question is going to be about which point. Well, we sum moments where we have the most unknowns. So in here, this one easy point over here, if I sum moments at point D, both CD and DH intersect that point. Okay, so they're not going to generate a moment. We can solve for GH. So the moment due to the force GH above point D is going to be the force GH times the distance, which is 4 meters. Okay. Now what is the sign? Well, if I'm pinned here at D and this force passes through the bottom, hopefully you can see that it's going to create a clockwise rotation. So that's a negative. What else can create a moment? Well, we have this force, but if we follow the line of action, it passes through point D, so it cannot generate a moment. So that's it. The only force here that can create a moment above point D is the GH. There's nothing else, so guess what? This guy has to be 0. The only way that is possible is if GH is actually 0, or if 0 force member. Now let's check our previous answers. We got GH equals 0. GH equals 0. Agreement. So we have GH now. Next, let's solve for, GH. Next, let's solve for CD. How are we going to do that? We could go to the sum of the forces in the X. I would prefer you not do that, and instead we sum moments at another point. Hopefully there's another point where two unknowns meet. Well, take a look at this. We have DH and GH, and although we have those values for those two, the two forces intersect at point H over here. So if we sum moment at point H and make it equal to 0, we'll have one equation with one unknown, right? So here, the moment due to force CD, force is CD, the distance is 4 meters, right? If we're here at point H, that force crosses through the top, that's going to create a positive moment. Oops. What else? Well, the 82 doesn't pass through point H, so it will generate a moment. 82.735 is the force. The distance is going to be 3 meters, and it will also cause a counterclockwise or positive rotation. Remember, we always stick into our convention that counterclockwise is a positive moment. I don't see any other force that will create any moments at point H. So that means the sum of these two must be equal to 0. We can solve for the force in CD by moving this to the other side, and we would get negative 82.735 times 3 divided by 4. This equals minus 62.051. Now let's check our answers before. 62.052. We're off by 1/1000th of a Newton, right? Just rounding errors. But take a look at the beauty again. What I like about the method of sections is we can check our work. How do we check our work? Well, we still haven't used this equation over here. So if we sum forces in the x direction and make it equal to 0, right? We should be able to check our work. So what do I have in the sum of the forces? Well, I have minus CD, I have minus GH, and I have minus DH times 3 by 5, right? That's the horizontal component. I got no other horizontal forces, so I gotta make them equal to 0. So now let's go ahead and substitute the values. Minus CD, but CD is a negative, right? So this is gonna become positive, plus 62.051 minus GH, so GH is 0, minus DH, so DH we figured out to be positive, minus 103.419 times 3 by 5 equal to 0. So look at this, 103.419 times 3 divided by 5 equals 62.051. So positive minus equals negative, positive minus 62, they cancel each other out and we got 0. So again, the beauty of the method of the sections is most of the time we can write a single equation with just one unknown. So that's going to boost our confidence in the values of those forces. And then we can also, most of the time, check our work by summing forces in the x or summing forces in the y and verifying. So that's another reason why I like this method a lot. So we've done 3 cuts already to the truss, all vertical cuts, and we have been able to determine the forces in these 3 members, this 3 members, and these 3 members, right? And we're still missing everything that is vertical because we haven't cut through them. You might be tempted to say, well, just let's cut the truss here in half. What would happen when we cut this in half, right? We would be exposing not only this one, but all of the members that we cut through. And it's going to look complicated. Plus, we're cutting through 4 unknowns, so we're not going to be able to solve it. So here, what could we do? Well, since I want this one here, how about I take a cut at another orientation? So let's maybe take a cut like that. See, if we cut like that, I'm crossing through 1, 2, 3. I already know the forces for those 2. And even if I didn't, I could solve it because I would have 1, 2, 3 unknowns. So let's take a look at what would the Freebody diagram for a slanted section would look like. Now, before we look at the Freebody diagram, we have to pick sides, right? Which of the 2 sections are we going to do? Are we going to do this left-hand section or the right-hand section? What is the difference? Well, the left-hand section, the geometry, it's less. I have less members than the one on the right. So it might seem like more simpler to draw, right? There's more members here on the right. However, if we look at the section in the right, we only have, look at this, 1 applied load over here. There's no other applied forces to the thrust. So if I choose the section here towards the left, I only have to worry about that 1 force. So I would argue that the left-hand section, although it's bigger, it's simpler to do an analysis because there's less forces. You can, if you want to, pick the section over here. I'm sorry, the right hand. You can pick the section over here on this side, get the same answers, right? It's just going to be more complicating, more accounting to do with the more forces. So I'm going to pick the section over here on the right. What does the free body diagram look like? Let me start here with like point D, and then I would be cutting through CD. This one goes to E, comes down, something like this. You have from E to G. Okay, that's this guy. And then I have D to G. Perfect. Look at this one, D to H. So that still makes the free body diagram, because again, I'm cutting here to this line. It's between H and A, right? So there's a little bit here that I cut through, and there's a little bit of this vertical member right here from H. So I'm gonna draw the whole thing, right? This was like this, and what we're saying is we're cutting here slanted like that, so I get to erase this here. So that's what the outline more or less looks like. Let me put here point F. That's the outline of the body, right? Next, we're gonna put the applied load. So at G, there's 82.735 newtons. That's the only applied load here on this left-hand section. Next, we would put any reactions or unknown. So we would have this guy, which I'll call AH. This guy over here, which is CH, and I'm going to assume an arrow pointing up, CH. And then we have this horizontal one, CD. Remember, if we extend the line of action of those two forces, they would be intersecting this point C. Finally, we need some geometry in this free body diagram. Right, the height here is 4 meters. And each of the bases here from point to point is 3 meters. This one here, this force points towards infinity. There's no need to put this point A over here. Okay, so we got outline, applied loads, reaction forces, we got geometry. What else do we need? An axis. So I'm just going to put here X. And maybe here to H. I'm going to assume this would be like my origin. Again, it doesn't matter. All I'm saying is X is in that direction, Y is pointing up. We draw this free body diagram. Yes, I already previously determined member CD and AH. This guy and this guy. So I could use that to build this free body diagram. That's one way we could go about it. Notice here AH was in tension, so AH should point away. Remember CD, we figured out that it was under compression, so this arrow really should point in that other direction. Again, I can draw the free body diagram like that and then just solve for CH. However, I'm going to treat it as a practice problem for you. Maybe in this question, all they wanted was CD, CH, and AH, so I would have cut like this, and I'm just going to practice again solving for the 3 unknowns on this section. So how do I do it? I'm going to look at it. I know I have some of the force in the X and the Y in a moment, so I look at it, and AH has a horizontal, CH vertical, CD horizontal, right? So right off the bat, I can solve for CH in this free body diagram by summing forces in the Y direction. Sum of the forces in the Y direction must be equal to 0. What do I have? Well, CH pointing up. That was my assumption again, because I'm assuming tension on this guy. And as I look around any other forces, the only other one is this guy over here, the applied load at G, which is 82.735. That guy points up. There's nothing else, so the sum of the forces must be equal to 0. What this is going to tell me is, when I solve for CH, I'm just going to move it to the other side, and we're going to get that CH is under 82.735. That's a negative load, so it would mean compression, right? 82.735, compression. So see how quickly we solve for CH? Let's practice solving now for CD and AH. I know we have the values already, but why not? Let's try to solve them over here. How would I try to solve? Well, both AH and CD are in the horizontal line along the X, so I wouldn't use the sum of the forces in the X. Instead, I would try to sum moments where I have two unknowns intersecting. Hopefully you can see that I got these two pointing here at point C. So one natural thing to do would be just to sum moments at point C and make them equal to 0. Come on, move over here. Sum of the moments at point C equals to 0. Again, I'm looking at this point. These guys don't contribute. AH does not pass through point C. So it can generate a moment. The force is 8H. The distance is 4 meters. Right? And if we're pinned at C and the force passes through the bottom over here, it's going to generate a clockwise or a negative moment. Next, we have the applied load 82.735. It's at a distance 3, perpendicular distance, that's a moment arm to point C. So times 3. Now this force, when it passes, is going to go up over here. So if I follow with my right hand, that's going to create a counterclockwise or a positive moment. I got nothing else, so the sum of those two moments must be equal to 0. So we can solve for AH quickly. I move this to the other side, becomes negative, so I'm going to have minus 82.735. Let me get my calculator. Minus 82.735 times 3 divided by a negative 4. So negative divided by a negative, that equals a positive, and we get AH equals 62.051. As I come and look over here, I had already determined that positive is tension, so it's good. Again, that's what I like about the method of the sections. I can cut this truss in a lot of different ways to solve for the same one, so there's usually more than one way to solve the problem. I can look at different free body diagrams and I can check for agreement so I can boost my confidence that I'm solving the question correctly. Anyway, so I have value for AH. What would I do next? Well, I would try to sum moments at another point where two unknowns intersect. Can you identify that point? Yes, right? We have CH and AH. The letter H is common to the two members, so it means they're crossing through point H over here. So if we sum moments about point H and make it equal to 0, what do we have? Well, we have CD up on top. This is H. CD passes through the top, so it will create a positive moment. We have CD. The distance to CD is going to be 4 meters. That's a positive moment. And then we have this 82.735. It's at a distance of 3 meters, 2.8, and it's also generating a positive moment. There's nothing else over here, no other external load, so the sum of those moments must be equal to 0. We can solve for CD very quickly. I'll move this to the other side and we'll have minus 82.735 times 3 divided by a positive 4. And what we get is minus 62.051, or that member CD is under 62 newtons in compression. Look at the CD, 62 in compression. Again, we get agreement. So right now we have agreement between method of the joints, method of the sections, even agreement for the same members with two different sections. So I really don't have to try to recheck this again. As I'm looking at the truss, there's other members that I haven't really checked. Right, I have this one that goes from D to G. How would I solve for that one? Again, I would draw over here or cut a section here, just like this one, but offset 3 meters, and I would be able to solve for this guy. I can do another section here if you want to, and you would have only a point with forces away. At that point, that would look exactly the same as doing the method of the joints here at F. So I think I'll go ahead and stop it here. With the method of the sections, I don't want to carry this video, longer than it has to. All I want to do is remind you, when we're doing the method of sections again, you're cutting the truss. So you make the cuts, and then you draw the proper free body diagram. Again, the outline, applied forces, any reaction forces, geometries, X and Y axis, right? Whenever you make the cut, just make sure you're cutting through 3 members, and you're going to be able to solve it every single time. Again, you want to strive for one equation for one unknown. So you want to look at where the forces are going. See if you can solve one quickly by summing forces in the Y or summing forces in the X. Next, you're going to sum moments. You want to sum moments at points where you have 2 unknowns. In this case, point H and point C. So one tip there is draw your arrows here and extend your line of action. So draw these dots and this one over here, so you can verify, hey, they're going to meet at point C over here. That's a good point. So try to sum moments where you have the most number of unknowns, so that you have one equation, one unknown. If you end up that you can't do that and you have 2 equations, as long as the same 2 unknowns are appearing in the 2 equations, you can solve them simultaneously and still get an answer. And so I think that's it for the method of the sections. I hope you found this video useful. If you picked up on any mistakes while I was doing this, do let me and everybody know in the comments below. Otherwise, we'll see you on the next one.